Okay, let's work through this chemistry problem. So here we have our equation. The change in energy is equal to negative 2.18 times 10 to the negative 18th joules times the product of 1 over n final squared minus 1 over n initial squared. In addition, we have this other equation, which is actually the Planck-Einstein relationship. It says that energy is equal to Planck's constant times frequency, which is also equal to Planck's constant times the speed of light over wavelength. Okay, so the question is asking, calculate the frequency of light emitted when an electron in a hydrogen atom makes each of the following transitions. Here, the first one gives us, it's going from energy level 4 to energy level 3. Okay, so this gives us two of our n's that we need. Here we have delta E is equal to negative 2.18. This is just the equation up there. I just rewrote it. And here, the next line, I rewrote the same exact equation, but instead of having n final squared and n initial squared, I had our n final and n initial plugged in. Our initial is 4, since that's where we start off, and our 3 is our final, because that's where we end up. Okay. In addition, I'm actually going to do two steps at once and do all the math and just one problem in our calculator, because we're saying that E is equal to all this. There's no more variables in this side of the equation, so this is just a constant that we can plug in for E, any other equation that we find E in. And since we're going to transfer that to frequency, we can find it in this equation right here. So since V equals frequency, what we're going to need to do is take the value that we got for E and set it equal to Planck's constant times the frequency, which I've done right here. So E is equal to HV, therefore, this value for E that we just got right here, all I did was solve 3 squared and 4 squared, is equal to Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds times frequency. Okay, here we have the entire equation filled out, because this is not solved for V, so all I did was divide this side by Planck's constant, which puts V by itself. So you can see this is the same exact thing we have right here, which is the same exact thing as here. It's just put on the top of the equation. I had something multiplied by V, so I divided it instead. After plugging all the numbers in, you get 1.60 times 10 to the 14th. This is actually in your calculator as negative, but since it's asking the frequency of the light emitted, this actually solves for energy. And since we're losing that much energy, it's actually negative, but we don't want it as a negative value. So whatever your answer is, just make it positive or multiply it by -1 if you want to do that. It's also important to note our units here. We have joules over joules, and that cancels out, but we have seconds on the bottom and no seconds on the top, so we have seconds to the -1. And the way you can think about this is that this is the frequency. So this is how many waves per second we're getting. So we're getting 1.60 times 10 to the 14th is the amount of times the wave does that per second, from trough to trough, or from the, I forget what the top is, but I think it's crest to crest. It does that little motion there this many times per second. And since this is the frequency, we're done with our answer because it asks us to calculate the frequency. If need be, we could take this and find the wavelength as well by setting the HV value equal to HC over the wavelength. But this is all it asks for, so we're done.